Greetings, everyone. This is Jared Lavador, and this is our PowerPoint presentation in Mathematics in the Modern World, entitled Rhythm of Life by Iron Stewarts. So these are my members: Jack Dasilcio Bargamento, JV Ingaling, Kim Abad, and Carl Andre. So I'll start our presentation. So once again, this is Jared Lavador. So, what is rhythm of life? Rhythm is an environment or sound patterns that can be found in every environment. In our daily lives, we encountered patterns, and our bodies have their own sets of patterns. So, in our daily lives, we encounter sets of patterns. Daghan taog na-encounter nga patterns like wala ta kabantay na patterns dito. So, proceed go. Many of the nature's rhythm are like the heartbeats. They take care of themselves. So, ang nature sa atong heart, sila ang mo take care sa ilang kaugalingon. Like, they beat according to pattern. So, na famous photographer who discovered an art and also a science. So, let's know about him. So, who is Edward Maybridge? So, Edward Muybridge is a photographer who was born Edward Mugridge but changed his name into Edward Muybridge. Photograph the different phases of gaits of the horse by placing a line of cameras with the triple wires to truth past Stanford. It is said he won his bet. Whatever the truth of the story, we don't know that Maybridge went to the pointer the scientific study of gaits. So Edward Muybridge, siya ang famous photographer sa una na gistudihan ang gaits of horse, kung unsay parents nila and also their movements. And also, he adopt a mechanical device known as zeotrope to display them as moving pictures, a road that in the short order led to Hollywood. So Muybridge found both science and an art. So I said earlier that Maybridge found an science and an art in the same time because of device called zeotrope. It is the first picture is moving picture of the horse. So this is the picture called the galloping of horse. This is the one that Muybridge took, and this it's like a moving picture. So that is all. Jarek Bargamento, take it away.
Good day, everyone. My name is Jack Pergamento, and here I am. Gait analysis. There are two types of question about biology and gait analysis. Why do animals move? Why they move like that? Let's answer the question. How do animals move? Interest in animals' locomotion has existed since antiquity, indicated by the ancient Greek philosopher and scientist. Aristotle works the De moto aluminium on the motion of animals. In the 17th century, Italian physiologist and physicist Giovanni Alfonso Viril investigated the movements of animals' body in the context of mechanical principle. English photographer Edward Muybridge used the sequential photographs in the 19th century to capture the gaits of several species. His photography demonstrated, for instance, that all four of trotting horses' legs are off the ground at a particular movement in the gait. Why do they move like that? As viewed from evolutionary taxonomy, there are three basic forms of animals' locomotion in the terrestrial environment. First, the legged, moving by using appendage. Limbless locomotion, moving without legs primarily use the body itself as a propulsive structure. Rolling, rotating the body of the substrate.
Two types of line symmetry. What about reflectional symmetries of time? Those correspond to reversing the direction in which time flows, a more subtle and philosophically difficult concept. Time reversal is peripheral to this chapter, but it is an extremely interesting question which deserves to be discussed somewhere. So, why not here? The law of motion is semester under the reversal. What does it mean for a system to be symmetric under time translation? It means that is that if you observe the motion of the system and then wait for some fixed interval and observe the motion of the system again. If you again, you will see exactly the same behavior. That is a description of periodic os- oscillations. If you wait for an interval equal to the period to see exactly the same thing. So periodic oscillations have time translation symmetry. Thank you.
So hi, I am Carl Andre. Why do systems oscillate at all? As a condition change, a system that has a steady state may lose it and begin to wobble periodically. In 1942, the German mathematician Herbert Hopf found a general mathematical condition that guarantees such behavior. In his honor, this scenario is known as Hopf bifurcation. So maong mo escalate ang system kay if mag-steady na siya or nasa sa steady state, kay makuhaan siya or it may lose or begin to wobble periodically. So mauna ang behavior na na-discover ni Edward Hopf. So Hopf's approach, the physical interpretation of the mental picture is that the oscillation are very small to start with and stability become larger. For example, the sound made by a clarinet depends on the hoop's bifurcation. Hoop's bifurcation can be seen as a special type of asymmetry breaking. So the idea is to approximate the dynamics of the original system in a particular simple way and to see whether a periodic wave will arise in the simplified system. So hoops provide that if the simplest system wobbles, then so does the original system. So, state niya na if wobble ang system or ang simple nga system, simplified system, mas mawobble ang original system. So, that is all. Thank you.
Guys, good day. My name is GV Ngaling. Today I'm gonna talk about the 7 most common quadruple gates are truth, pace, bound, walk, rotary, gallop, transverse gallop, and canter. First one is trot. In trot, the legs effect link in diagonal pair. Second one is pace. First, the front left and back right hit the ground together. Then the front right and back left. And the third one is bound. In the bound, the front legs hit the ground together, then back legs. So the pace links the movements before and after. So two left legs hit the ground, then two rights. The fourth one is walk. So the walk involves a more complex but equally rhythmic pattern. So front left, back right, then front right, back left, then repeat. And the fifth one is rotary gallop. So the rotary gallop is the front legs hit the ground almost together, but with the right very slightly later than the left. Then back legs hit the ground almost together, but this time with the left very slightly later than the right. The sixth one is transverse gallop. So transverse gallop is similar to a rotary gallop, but the sequence is reversed for the rear legs. And for the last one, we have canter. So canter is even more curious. First, front left, then back right, then the other two legs simultaneously. There's also a rare gait, the pronk, in which all legs move simultaneously. Thank you.
So we've now explained that periodic oscillation possess time translation symmetry, but we haven't yet told you what symmetry is broke to create that pattern. So the answer is all the time translations. A state that is invariant under these symmetries must look exactly the same at all instants of time, not just intervals of one period that is or that is it must be steady state. The lesser message is that mathematics can illuminate many aspects of natures that we don't know or we do not normally think of being mathematical. This is a message that goes back to the Scottish zoologist D. Arkwright Thompson, whose classic but maverick book on growth and form set of in 1917. An enormous variety of more or less plausible evidence for the role of mathematics in the generation of biological form and behavior. So in the age when most biologists seems to think that the only interesting about an animal is its DNA sequence, it is a message that needs to be repeated loudly and often. So once again, this is Jared Lavador and thank you for listening. Goodbye.